Hello, welcome to the online recording for tutorial 10. Now today I'm going to talk about one of the very important things on what is called tutorial 10, which is on the topic of collision. But however, prior to completing what we know as tutorial 10, I would like to first of all do a bit of explanation or re-explanation on the concept that I've done in tutorial 9, because I know that for tutorial 10, for tutorial 9, the recording quality was not that good. And there are some problems in terms of the cursor, and there are problems in terms of the audio. So I would like to do a bit of quick recap on what is being taught of the concept in tutorial 9, and also because tutorial 10, the understanding in tutorial 10 is closely related to what we have in tutorial 9. So in tutorial 9, we learned of something known as COLM, right? Conservation of linear momentum. So what is conservation of linear momentum? So according to the principle of conservation of linear momentum, it states that the momentum of a system is conserved if there are no external force, what's it called, acting on the system. So first of all, let's try to dissect what does this term mean. So momentum of a system is conserved if there are no external force acting on the system. So what is known as a system? So first thing, let's try to understand first what is actually a system. So a system, to put it simply, in a very, simplistic way, it's just a collection of particles or a collection of bodies. So for example, let's say if I have like 5 particles here, 1, 2, 3, 4, 5. A system depends on where do I draw my system boundary, and where will this system boundary be, to be honest, is purely arbitrary. So if today I were to draw my boundary across this particle itself, then this particle inside this boundary here is known as a system. So this particle inside this system boundary is part of a system. So if today I were to draw my system boundary across 2 particles, then these 2 particles inside this system boundary is part of a system, it's known as a system. So the system simply speaking, just a collection of particles, and that if I were to draw my system boundary across all these particles here, then all this particle is part of my system, all right? And that is basically literally just meaning a collection of the particle itself. So the first thing that we wanted to ask is basically what is a system, and we have answered it. It's basically just a collection of particles or bodies, and the idea of a system boundary depends on it depends on how do you draw. The idea of which particle consists of the system depends on how do you draw the system boundary. So sorry, let me just rephrase that. So the very idea on which particle belongs to the system depends on where you draw a system boundary. If today you draw a boundary across this one particle, that particle belongs to the system only. And if today you draw the boundary across all the particles belongs to the system. It's very arbitrary, it depends on where do you draw the system boundary. Now, let's talk about what does it mean by external force. So, external force, to put it very simply, are just forces which is acting on the system, but is originated from a particle or a body that is outside the system or not part of a system. So what I'm trying to say. So for example, let's say today my system boundary was drawn across these 2 particles here. Now, these 2 particles here, because it's a particle, it might exert a force in all directions. It might exert a force on other particles, right? So let's say this particle here might actually exert a force on this particle, exert a force on this particle, on any particle in all direction. This particle might also exert force in all direction, right? So the forces, these red color forces, which are caused or originated by the particles inside the system boundary, are known as these are not external force. These are known as some sort of an internal force. In other words, these forces are forces originated by particles inside the system. Okay, they're originated by particles inside the system. Now, however, if today we are talking about the forces which are originated from this particle outside the system, and these forces actually directly affects this particle inside the system. Now these forces, not apart from these two one, so let's say we have these forces which are caused or originated by particles outside the system, and they directly influence the particle inside the system. Now these forces are known as external force. So external force are forces which affects the system or that is imposed onto the system and originates from particle which is outside the system. Let me repeat, what is external force? External forces are forces that are imposed onto the system by a particle which is not part of the system. So let's say for example, right, just a very quick example. Let's say we have this particle, let's say we have this particle. This particle is inside the system boundary. And if, let's say, this particle exerts a force on this particle here. Now, is this force considered as external force? No, it's not an external force, because although this force is imposed onto another particle inside the system, this force is actually originates from a particle inside the system. So this is an internal force, it's not considered as an external force. However, if today we have a force, let's say this red color point, a force which is originates from a particle inside the system, this force which originates from the particle inside the system, and it actually exerts a force on a particle outside the system, this is also not considered as an external force, because first of all, it originates from the particle inside the system. Second of all, it actually affects a particle outside the system, so it's not considered an external force as far as this system is concerned. However, if today we are talking about the forces which originates from this particle, and or forces that originates from this particle, and this force actually affects or is imposed onto a particle inside this system. Now this red arrow force here is considered as external force, because A, it is originated from a particle outside the system, and B, is actually acting on a particle inside the system. Alright, so it actually depends on where do we draw boundaries, and how do you define the boundaries, and how do you actually denote which is considered as an external force or internal force. So to make this more clear, let me just try to do a bit of explanation. So let me just wrap this off. So the explanation I would like to do is that imagine in this universe there are no other planets, and there's only three particles. First particle is red particle, second particle is a blue particle, third particle is a green particle. Alright, and this red particle actually exerts a force on this blue particle, and it exerts another force on this green particle. So basically the particles will exert forces on their neighboring particles. So this green particle will exert a force on the red particle, this green particle will exert a force on the blue particle, and again this blue particle will exert a force on the green particle, this blue particle will exert a force on this red particle. Now, so as far as I can tell, so the color of the arrow indicates the source of the force. Alright, so means red arrow indicates the forces originates from the red particle, blue arrow indicates forces originates by the blue particle, green arrow indicates forces originates by the green particle. So that's what we need to know. Now, if today I were to draw my system boundary across this red particle, and as I said, this system boundary is completely arbitrary, depends on what I like. If today I want to draw a system boundary across that surrounds this red particle, it means that in this case only the red particle is part of my system, the blue and green particle are not part of my system, and hence when I were to draw my boundary in this manner, it means that this blue color force and this green color force, now these two forces are considered to be an external force. Very good. These two forces are now an external force with respect to this particle, this system, because these two forces are originated from particle which is outside the boundary, and it actually affects or is imposed on the particle inside the boundary. So in this case, we can say that the momentum of this system will not be conserved because there is external force. The conservation of linear momentum states that the momentum of a system is conserved if there are no external force, but in this case there are external force, so In other words, momentum is not conserved. When momentum is not conserved, it means that the mass of this particle times the velocity of the particle when t equals to 0 is different than the momentum times the velocity of the mass times the velocity of this particle when time is equal to, let's say, t1 in the future or t2 in the future. Alright? So now, however, if today, let me just knock this off, and let me just redraw the let's just redraw this thing. And now, let's say today I were to draw my system boundary across all of the particles itself, Now, in this case, it is very apparent. It is very apparent that, first of all the particles are inside my system boundary. When all the particles are in my system boundary, I can confidently say that there are no external force acting on this boundary, right? Because first of all, if you can see, there are no external force acting by any other particles outside this boundary on the particles inside the boundary. So there are no external force. So it means that the momentum of the system is conserved. So what does it mean by momentum of system is conserved? It means that, let's say, so the mass of the red particle times the velocity of the red particle when t is equal to 0 plus the mass of the particle, the blue particle, times the velocity of the blue particle when t equals to 0 plus the mass of the particle and the velocity of the green the mass of the particle times the velocity of the green particle when t equals to 0 is equals to the mass of the red particle times the velocity of the red particle at some time in the future plus the mass of the blue particle times the velocity of blue particle sometime in the future plus the mass of the green particle times the velocity of the green particle sometime in the future. So it means that the momentum of a system, in other words, is conserved. It's all conserved. So we don't have to worry about anything in this case. Now, this is a very fundamental understanding of conservation of linear momentum, and as I said before, the idea of conservation of linear momentum is very specific in terms of the external force. So let's say today I have a particle here, and let's say this particle here, and let's say I have I assume this particle to be a system. I draw my system boundary across this particle. Now, if today there is an external vertical force acting on this particle, there's an external vertical force acting on this particle, it means that momentum of this particle is not conserved vertically, but it is actually conserved horizontally. It means that the mass of this particle, so I'm just use a red, black pen. The mass of this particle times the vertical the vertical velocity of this particle is not equal, when time equals to 0, is not equal to the mass of this particle times the vertical velocity of this particle when time is equals to 1, when t1 in the future. However, the mass of this particle times the horizontal velocity when t is equal to 0 is equal to the mass of this particle times the horizontal velocity when t is equals to 1 in the when t equals to t1 in the future. So the idea of the subscript of 1 and 0 indicates the velocity at some time in the future and the initial velocity respectively. Okay, repeat. So let's say I have the particle here, and that's a vertical external force, but there are no horizontal external force. It means that the vertical momentum is not conserved. In other words, the mass times the vertical velocity when t equals to 0 is not equals to the mass times the vertical velocity when t is equal to some time in the future, denoted by v1. And however, the horizontal velocity when t equals to 0, denoted by vho, times the mass is equals to the mass times the horizontal velocity when t equals to 1 in the future. Alright? So it means that in this case, vertical velocity not conserved, horizontal velocity is conserved. So this is one of the most important things in tutorial 9. Now, let's talk about tutorial 10. So in tutorial 10, we are just introducing something known as collision. So the idea of collision is very interesting. So it just means that what it's trying to say in the idea of collision means that when two objects come close to each other and they actually have a very short amount of time in contact and they separated from each other. So in this case, let's talk about in terms of force. So force is equals to rate of change of momentum, right? So force is equals to dl, where L equals to momentum, over dt, or just to be more exact, net force. Net force is the rate of change of momentum. So let's say today when I have a particle here, and I have another particle here. Okay, this particle actually moves in the reasonable speed, and it actually collides with this particle. So this particle moves here, this particle is constant, it is at rest, and this particle actually sort of collide with this particle. And after it collides, it actually bounces off. It collides and it bounces off. Collides and it bounces off. Now, at the very short, at the very short span of time during the collision, this particle exerts the force on this particle, and this particle also exerts the force on this particle. Now, mathematically speaking, we can always assume that this force that actually exerts on one another is very big. Okay, so why can we say the force is very big? Because first of all, we know that when this thing when this particle hits the other particle during collision, the time of contact between both these particles is very short. It means that this term is very small. The dt term will be extremely small. Okay, this is mathematically incorrect. So let's just put it in a more general form where most people will understand what I'm trying to say. So we can actually kind of like approximate this net force here with a change in momentum divided by a change in time. Okay, and as we can see, when this particle actually collides this particle, the change momentum will be non-zero. Right? It will not be very close to zero. There will be a change in momentum. However, the time taken for this change in momentum is very close to zero, right? Because the time taken for collision is extremely small. But the time taken for collision is extremely small. It means that the time period of the collision happening is very small, and it means that the collision force is very large. So in this case, when two particles actually collide each other, very important point, we have to assume that the collision force is so large that all other forces which are not directly involved in this collision motion can be ignored. Right? So let's say, because as we just proved, force is rate of change in momentum, right? And let's say we can approximate this term as a change in momentum divided by a change in time. Now, as we know, the change in time is extremely small. However, we know the change in momentum is not small, it is non-zero, because when the momentum change from one to another, it is not a small change in momentum. It can have a large change in momentum, just like a ball bouncing off across a wall, right? So it means that the net force acting on both these bodies is extremely large during collision. So when the force acting on these two bodies during collision is very large, it means that during collision, the collision force is large, and that other forces which is not directly involved in this collision motion can be ignored. Okay, so what do I mean by not directly involved in the collision motion? Okay, we will deal with that later. We will deal with that last later. But first of all, let's get the concept straight first. First of all, understand one thing. Number one, in collision, the collision force is very large. So the first thing first is like, how do we actually investigate properties involved in collision forces when we assume that the collision forces are so large? If the collision forces are large, it means that we could not actually use the idea of F equals ma, right? Because F will be infinity and ma will be something that's hard to determine. And during collision, we do not know is there a deformation in terms of this particle itself, and how does the particle respond? Is the acceleration constant? We can never know that, because first of all, the collision force is too large and time is too small, and it's hard to differentiate. It's hard to identify those properties. So, in order to investigate collision, first of all, we always want to use the idea of momentum. We always want to use idea of momentum. So, in other words, we will always try to apply conservation of momentum when we are trying to solve collision problems. But the problem is that we could not always just anyhow apply this momentum equation, because, as we say, the conservation of momentum equation is only applicable when there are no external force, and the idea of external force depends on where do you draw the system boundary. So, apart from using this momentum equation, there's another important concept that we actually introduce in this chapter to describe the effect of collision, and that very concept is known as the coefficient of restitution. Alright, so this understanding, this idea of coefficient of restitution was introduced because it's actually very tough for us to investigate what is going on in the Newton's second law manner in terms of during a collision. It's very hard for us to see what's going on with the force and acceleration response. So in other words, to describe the motion just right before and after collision, we use something known as the coefficient of restitution. So this coefficient of restitution understanding, you don't have to know how does it originate, you don't have to know what's the main reason of it, but in other words, it basically evolved in the change of kinetic energy which is available inside the particle or inside the body before and after collision. Let me repeat, the coefficient of restitution some sort of explain or encapsulates the what is called change in kinetic energy of a particle before another collision. You can think of it as the equation of coefficient of restitution actually describes that. So, but right now it's just not important, because at least in terms of exam or in terms of tutorial, what they will always provide you with what is actually the coefficient of restitution. Okay. Now, for coefficient of restitution, it is important to know that excuse me, the equation. So what is the equation for the coefficient of restitution? So before I explain, just take a look at the equation first. The equation of coefficient of restitution states that the final velocity of a particle, let's say this particle is particle A, this particle, it says that VAN1 minus VBN1 is equals to negative E VA0N minus VB0N. Okay, so now this looks very intimidating. What does this term actually means? So first of all, I'm going to introduce to you what this term means and how do we actually explain this term term by term. So let me just get to the bottom of this very quickly. Okay, so let's do a bit of let's redraw the term, what's it called, particle. Let's say I have particle A, and let's say I have particle B. Okay, I have particle A and I have particle B, and particle A and particle B actually collides at this very point here. So before collision, particle A definitely has a velocity, and before collision, particle B definitely has a velocity. Now, what is the velocity of particle A and particle B is not very important. However, in order to use the coefficient of restitution equation, when we were to describe the motion of particle A or the motion of particle B, we have to resolve the velocity of the particle into two different directions. One direction which is along the plane of collision, the other direction which is perpendicular to the plane of collision. So the plane of collision can be denoted by this red color dotted line here. This is my plane of collision. Let me just repeat. So this is my plane of collision. Okay, this is my plane of collision, and apparently if we use this black color term, I always denote this direction along the plane of collision is known as known as ET, where ET denotes a unit vector along the direction of plane of collision, and EN denotes the unit vector along the perpendicular direction of the what is it called, collision plane. So what I'm trying to say here is that, so I know it's a bit fuzzy here, but just try to absorb what I'm trying to say one moment at a time. So as I said before, to use this equation for coefficient of restitution, we have to resolve the motion, the velocity motion of particle A and B in the ET and EN direction. And the component of velocity in the EN direction is what is the term that we use inside the equation of coefficient of restitution. So what do I mean? It means that, for example, let's say that velocity of A, let's say A, VA, before collision is a certain number. So the velocity of A before collision, denoted by this zero here, must be resolved into the normal direction to the collision plane, and it also must be resolved to a tangential direction, which is along the the velocity of particle A before the collision must be resolved. Velocity of A in the the velocity of A in the before the collision must be resolved in the velocity direction, which is perpendicular to the plane of collision, and to another direction which is parallel to the plane of collision, denoted by this term. So this term denotes the velocity component perpendicular to collision plane. And this term denotes velocity component parallel to collision plane. Okay, how do you get this term? We will talk about it later. But this VAOM, which is the magnitude of the velocity component perpendicular to the collision plane, is actually equals to this VAOM used in this equation of coefficient of restitution. Alright, and subsequently, for the velocity component after collision, which is denoted as VA1, which is the velocity of particle A after collision, must also be broken down into the normal direction to the collision plane plus the parallel direction along the collision plane. In other words, the final velocity of particle A after collision must also be resolved into the normal direction to the collision plane and the parallel direction along the collision plane. And this term precisely was used here in the equation of coefficient of restitution. And using the same understanding, we can actually know the velocity of B before collision must also be resolved into the VB1 direction, VBO direction, which is normal to the plane of collision, plus the VBO direction velocity component, which is tangential or parallel to the collision plane. We also know the velocity of B, particle B after collision, must be resolved into the velocity of B1 normal to the velocity of B normal to the collision plane, and must also be resolved to the velocity of B1, which is perpendicular parallel along the collision plane. Right, so very important. So VBO denotes the velocity of particle B after the before the collision, and it must be resolved into two directions. One is perpendicular to the collision plane. One is along the collision plane. The velocity after collision must also be resolved to the direction which is normal to the collision plane, and the direction which is parallel along the collision plane. Now, and apparently this VB naught here, VB naught n here, was actually used in this part of the coefficient of restitution, and this VB1n, this term here, was used in this part of the coefficient of restitution. So that's how all this term in the coefficient of restitution comes about. Okay, it comes from resolving the velocity component of each particle before and after collision along the direction of collision plane and perpendicular to the collision plane. And the component of velocity, which is perpendicular to the collision plane, was all used to describe this component inside the equation of coefficient of restitution. Now this E will be given to you as something that must be given to you, is measured experimentally, is something that you can derive yourself. So we're cool with that, right? So in other words, in this in this tutorial itself, we actually learned a new equation, which is the equation of the coefficient of restitution, and each term in this equation of the coefficient of restitution was obtained by resolving the velocity into a tangential component, into a component which is normal to the collision plane, and to a component which is along the collision plane. And please take note, this is a very important tip. This ET direction and this EN direction must be consistent throughout your question. If your question you use ET to be in this direction to calculate for VAO, you must also use ET in this direction to calculate for VBO, for VB1, or for VA1. Same thing goes to EM. In other words, the unit vector in the direction of the unit vector of the unit vector of the direction perpendicular or parallel to the collision plane must be consistent throughout you solving the question. So I know most of you will be quite confused by what I'm trying to say here, so but it's okay, it's fine, no problem. Let's just try to solve a problem. Okay, let's try to solve a problem, and by solving the problems we can actually know what is going on with these questions here. So now let's take a look at the first question, tutorial 10, question number 2. So this is a very simple question actually. The ball is dropped from rest and falls a distance of 1.2 meter before striking the smooth plane of A. If E is equal to 0.8, determine the distance D to which it strikes the plane again at B. Okay, so first of all, this thing drops, right? When this thing drops, eventually you will have a vertical velocity when you reach the plane. After it hits the plane, it will actually bounce off, right? So as we can say, let's assume that this is A. This ball is known as particle A, and this block here, this ground here is known as particle B. Now apparently, the ground is not going to move, so we can say with confidence, velocity of B before collision is equal to 0. Velocity of B after collision will also be equal to 0. Now, let's try to find velocity of A before collision. Velocity of A before collision is definitely a number, and it is actually, that must be negative 90 degrees, right? And it must have a number. So what is this number? What is the magnitude of velocity of A before collision? Now apparently, you see this is fall from rest, and we can use the conservation of energy equation. So in other words, the final kinetic energy FMA, final kinetic energy VA naught square, so this is definitely VA naught in terms of magnitude. The final velocity, the final what is it called, kinetic energy of the particle A is equals to the initial potential energy, gravitational potential energy, right? So we can cancel MA here, and we can find that the initial kinetic so we can find the velocity prior to collision is equals to 2gh squared. And if you use a calculator, 2gh squared is equals to 2.9.81 and times the height, which is 1.2. We square root them, we get 4.52, which is 4.852. So this is actually 4.852 meter per second. So I'm just check again my equation. Okay, so we have it. So in other words, we know the velocity of A, O, before collision is equals to 4.852 direction, negative 90 degrees. Now, as I said, for all collision questions, it's important for us to use the coefficient of restitution equation because there is a coefficient of restitution given to us. So to use this coefficient of restitution equation, we always want to resolve velocity into the tangential to the what is it called, collision plane direction, and normal to the collision plane direction. So in this case, the collision plane, apparently, this is the collision plane, right? So this is the collision plane, this is the collision plane. So apparently this is the collision plane. If this is a collision plane, I can actually denote this one as my the unit vector normal to my collision plane, and I can denote this direction. Oh, sorry. I can do this direction as the tangential direct, the unit vector tangential to my collision plane. Now, obviously, the unit vector that's normal to my tangential plane can be in this direction too, doesn't matter. And the unit vector of tangential to the collision plane can be in this direction. It doesn't matter. As long as you consistently use that direction throughout the question, you will be fine. So, first question first, let's try to understand this. So what we're trying to say is that velocity of A naught, we must try to represent it in terms of a component which is normal to the collision plane, and one direction which is parallel to the collision plane. So what is EM? EN is basically this angle here, right? EN basically denotes the direction along this angle here. So this angle here can be actually calculated out. So let's just try calculating out. Okay, so first of all, we can see that this angle So if you use some trigonometry manipulation, we can know that this angle here, so just bear with me, through some trigonometry manipulation, we can see that this angle here is equals to 36.87 degrees. So this angle is 36.87 degrees, and so we know that this the angle here, theta, is actually equals to 90 minus 36.87, which is just 53.13 degrees. Now, how do I get this angle direction? Well, it's just purely based on geometric method. So I'm going to leave it to you to find out how to actually find this what is it called, this direction. But in this case, we have established, or we can establish that EN in the normal direction is actually 53.13 degrees, and that the tangential direction ET is equals to so this EN is equals to a direction, so it's not just, so it's a direction which is 53.13. Just mark it out. It's equals to a direction which is 53.13 degrees, and ET is a direction which is negative 36.81 degrees. Right? You see that? So we have managed to establish that EM is in this direction and ET is in this direction. So in other words, we are trying to find this one, which will denote us VAON. EN is equal to direction 53.13 degrees, and VAOT is equals to negative 36.81 degrees. So we know that we want to find the component of this initial velocity along 53.13 degrees and along negative 36.1 degrees. So how do we do that? Now, here is something that's very important. Now, please take note how to find VA naught N and VA naught T. So in other words, VA naught N is equals to the component of the initial velocity prior to collision of A in the direction which is normal to the collision plane. So in other words, it's just a matter of resolving the velocity direction, velocity vector. So VAON is actually just equals to VAO, the vector itself, dot product with a unit vector N, EN, which is actually unit vector in the direction perpendicular to the collision plane. In this case, we can just do the whole mathematic. 4.852 direction negative 90 degrees dot product with direction 53.13 degrees, and from here we can easily get negative 90 minus 53.13 cos answer times 4.852. We got 3.8816 meter per second, right? And apparently that's the same way we are going to use to solve VA naught T. So how do you say VA naught T? VA naught T basically is the velocity direction of velocity of A naught in the tangential direction, which in this case we dot product with ET. Alright, to get the let me just a bit wrong. So let me just repeat. So we want to find the component of the initial velocity which is along the plane of collision, just equals to the velocity before collision dot product with the tangential, that unit vector tangential to the plane of collision. When you dot product them together, you will get the component of velocity which is along the direction of collision, along the plane of collision. In this case, we can do it directly. VAOT is equals to 4.852 direction negative 90 degrees dot product with negative 36.81, and in this case you will get negative 90 minus negative 36.81 cos answer multiplied by 4.852. we get this number as 2.907 meter per second. Okay. Alright, just need to retract my calculation, make sure that's correct. So now, we have managed to get VA naught N and VA naught T. Now I want to stress on how important is it to get VA naught N and VA naught T. So to get VA naught N, what you do is just that you take the initial velocity, the total initial velocity of A before collision, you dot product with direction, a unit vector in the direction perpendicular to the collision plane. That way you get VA naught N because it's a component of the velocity before collision which is perpendicular to the collision plane. Now, so we have solved VA naught N and VA naught T. Alright? So the next thing to do is that we want to use the coefficient of restitution equation. So first of all, definitely we have to find about VA1. So in other words, we want to use the coefficient of coefficient of restitution. So in other words, we also have to resolve our final velocity after collision in the EN and ET direction. So in other words, VA1, which is a velocity of the particle after collision, we can actually resolve it into a direction which is which is perpendicular to the collision plane, and to another direction which is tangential to the which is parallel to the collision plane. Now, however, it is impossible for us to find out these numbers. Okay, we know that EN and ET is equals to these two things, yes, but we can actually not find out this number in the meantime because of the limited information we have. So let's take a look at what are the information we have now. So what are the information we have now is basically this one. We have this information, and we actually have this information where VA naught, velocity of A before collision, is equals to 3.8816 N plus 2.907 ET. Okay, let me see if it makes sense. Okay, it makes sense. All right, this makes sense. Okay, I think I'm going to get a problem. Let me just to check my equation. Negative 90 minus 53.13 cos the answer. Oh yes, times 4.852. Alright, my mistake. There's a negative sign here. Yeah, so this kind of mistake always happens. Yeah, cos the answer times 5.852. Alright, yeah, sorry, my mistake. So please apply that. There's a negative sign here. Please take note there's a negative sign here. And there's a negative sign here means there's a negative sign here. Right, that makes sort of sense. That makes more sense. Now, so currently we have these two equations, and we also have the equation where VB1 is equals to 0 and that VB0 is equal to 0. Now let's see if we can apply the coefficient of restitution equation down here. To apply the coefficient of restitution equation, we know that the velocity of A after collision normal to the collision plane minus the velocity of B after collision normal to the collision plane is equal to the negative of E times the velocity of O before collision normal to the y is equal collision plane minus velocity of B O, which is before the collision, which is normal to the collision plane. Now we know that VB1 and VBO is 0. This is always 0. So it means that we can say that VB1N and VBON is also 0. So we can say this minus 0 is equal to negative E minus 0. Right? And what is VA1? VA1 N is actually this term here, which is an unknown. So we just place it at VA1 N. And what is VBON? VAON. VAON is basically just this term, right? This term is VAON. Remember this thing that we did here. So it's negative 3.8816. So it's just negative 3.8816. Now, doing this thing, eventually we can find the velocity of A1 normal, means the velocity of A1 normal to the direction of collision after collision is equals to negative 3.8816 multiplied by E. E is actually 0.8. E is 0.8. 0.8, and you will get 3.105 meter per second. Now, this is actually the velocity of particle A after collision, and this denotes the velocity of the particle after collision, but it's only VA1 at. It's not the total velocity of particle A after collision. It's the component of the particle of the velocity of particle after collision, which is normal to the collision plane. So in this case, it means that we know that VA1 at VA1 is equals to 3.1053 plus VA1T ET. Now to continue the question, we have to actually find out what is VA1T. So how do we find VA1T? Well, this is a very interesting part. Now please take a look at it. Now think about this, alright? Just take a look at this equation here, this part here. So this particle actually bounces off this particular plane here. Okay, let's just do a bit of comparison. Let's just draw this this thing. So let's just draw some shapes. Let's see if we can make it better. So, alright. So now ignore the other part of the shape. Let us only take note on this part here. So as we know, the particle actually bounces off this plane here. When it bounces off this plane here, it is extremely important to note that the forces acting by this plane on this particle is definitely in this direction, right? The collision force when the particle actually hits the plane is going this direction. The collision force of this particle, experienced by the particle when it hits the plane, is in this direction. In other words, if today I were to draw a boundary, I draw a system boundary across this particle, I can confidently say that the force experienced by this system is in this direction. In other words, there is no external force experienced by this system in this direction, which is parallel to the collision plane. Let me repeat. The external force is only perpendicular to the collision plane. There is no external force parallel to the collision plane as far as this particle is concerned. If today we draw a system boundary across this particle, we can see that there is only external force along the perpendicular at the direction perpendicular to the collision plane. There is no external force along the direction of the forces which is along the collision plane. Right? There's no external force in this direction. There is external force in this direction. So we can also say that momentum is conserved in this direction, right? If we draw the system curve around this, so we can say that the mass. So we can confidently say that the mass of particle A, the mass times the velocity of particle A before collision, tangential to the collision plane, is equals to the mass of particle A times the velocity of the particle A, the component of velocity of particle A after collision tangential to the collision plane. This equation was originated from the conservation of linear momentum equation. The conservation of linear momentum equation in this case works because there is no external force along the collision plane. And since we can see that MA and MA is the same, so we cancel each other, we can see that VAOT is equals to VA1T, and VAOT is equals to this term here, which is 2.907. Is equals to 2.907. So from these two equations here, we can finally say the velocity of A after collision is equals to 3.1053 En plus 2.907 Et. Right? That's how I find the final velocity of A after collision. Now, of course, in this question, they ask you to find the distance where it strikes plane B again. So this question, after you find the velocity of A after collision, you can use the Cartesian coordinate method to find what is the distance D. This one I leave to you to calculate. But first of all, let me just try to re-explain how do I achieve this final velocity of A after collision here. Now, actually, I actually employ two methods of calculation. The first method of calculation is using the coefficient of restitution. From the coefficient of restitution equation, I actually get VA1N, velocity component, normal to the collision plane after collision. And by using the conservation momentum of the system, by drawing the system boundary across only particle A, I actually can find out the velocity of A after collision, the component of velocity of A after collision, which is tangential or is along the collision plane. Right? So I know it's a bit hard to understand, but just let me just try to do a very quick recap. So what I do first, I use the equation of coefficient of restitution. That's the first thing I use. The equation, it's not just the red. So first thing I use is the coefficient of restitution. From the coefficient of restitution, what I found out was that I found out the velocity of A after collision, which is normal to the collision plane. After that, I employ conservation of linear momentum. And from this conservation of linear momentum, I found the velocity of A after collision, which is parallel to the plane of collision. Okay, and from these two things, I can get them together, and I can say that velocity of A1 is equals to VA1N En plus VA1 TET. Okay, so it is important to know that usually when we solve equations involving collision, we always use these two understanding. We always use understanding of coefficient of restitution. We always use the understanding of conservation of linear momentum. From both this term, we can actually find out the final velocity after collision. What we only want to find out is the final velocity after collision. But however, to employ the coefficient of restitution, we must make sure that we resolve our initial velocity into the normal direction, into a direction normal to the collision plane, and into a direction parallel to the collision plane. We also must resolve our final velocity after collision to a direction normal to the collision plane and to a direction tangential to the collision plane. Alright? So, in this case, we are lucky that we are doing collision between a particle and a static ground. In this case, the velocity of the ground after and before collision is always equal to 0. When it's 0, we can straight away put 0 inside the coefficient of restitution equation. If today we are not dealing with a collision between a particle and an object and a solid ground, rather it's a collision between two particles, in that case, we have to make sure that this term is non-zero. And since today, now this is very important, just take note. Since today we are doing a collision between the particle and the static ground, we can only apply conservation of linear momentum upon this particle here. It is actually impossible to encapsulate this particle and this ground here. If you assume that there's only an earth and this particle here, if you encapsulate all things and use conservation of linear momentum onto it, you wouldn't find anything, because first of all, you have no information on the mass of the earth. Second of all, you have no information on the approximation for the velocity of earth and stuff like that. So the only thing that you know is the mass of the particle here. And in that case, you don't know the mass of the particle is fine, but in this case, you can actually draw a boundary across this particle here. Now, some of you might ask, why during collision we can say that the momentum is conserved along this direction? Some of you might ask, why can we say the momentum is conserved along this direction? Because I say that there's no external force along this direction. And you might argue that there's actually a gravitational force, right? There's a gravitational force. This gravitational force can be along this direction. Well, the answer is that during collision, the collision force is so large that we actually ignore this gravitational force. Let me repeat, during collision, the collision force is very large, so we actually ignore this collision force. When this collision force is ignored, it means that there is no, when this collision force is ignored, it just certainly concludes that we assume that there is no external force along this direction, and there is no external force along this direction. It means that momentum is conserved along this direction. We can use this CORM here. So next, let's go to the next, tutorial. Okay, so let's go to tutorial 10, question 3. So I hope that, so for the previous question is a bit fuzzy. I think my explanation was a bit fuzzy, so I hope that I can make it up to you in this explanation now. So in this explanation here, we have two identical billiard balls which may move freely on a horizontal table. So this is a horizontal table, so it was trying to tell us that we can ignore gravity, we can ignore the normal force on the horizontal table because they will cancel each other. So ball A has a velocity of v naught as shown in here, and it hits ball B, which is at rest. And at a point C defined by theta equals to 45 degrees. Okay, so they basically hit at this point here. So this theta is 45 degrees, trying to give you an understanding on where is a collision plane. So apparently the collision plane that we are talking about is in this direction. This is the collision plane. This is the collision plane. Okay, it's a bit hard to draw. This is the collision plane. Okay, now knowing that the coefficient of restitution is 0.8 and assuming no friction, this means the velocity of ball after impact. So this is a very interesting question. Actually, it's a very common question in terms of collision questions. So let's try to solve this. Okay. So first of all, we want to know what is the velocity of each ball after the impact. So when we are given the coefficient of restitution, definitely we have to use the equation for coefficient of restitution. And to use the equation, definitely we have to resolve the velocity of A and B before and after collision in the EN and ET direction. So the first thing we do always for a collision question, the first thing we do is that we always try to find out what is our EN and ET direction. So in this case, I denote this as my ET direction, which is parallel to the collision plane. I denote this as my EN direction, which is normal to my tangential plane. And by some calculation, I can confidently say my EN, at least according to my EN as a unit vector, is in the direction of 135 degrees. Right? So it's 180 minus 45 degrees. So this direction here. This is my EN direction. And my ET direction is equals to 45 degrees. So this is all basically very geometrical. You can find it out yourself. ET is this direction, ET is this direction, and EN is this direction here. Okay, now what is important is that we have to know how do we solve the question here. Now to solve this question, the first thing that we do, the very first thing that we do is that we try to find out what is VA naught. So we know that VA naught is equals to V naught. Okay, you say a velocity of V naught and it hits ball B. So V naught is going horizontally to the right, so it's at 0 degrees. But of course, we are not satisfied with the idea of V naught here, right? We want to put it in terms of N, and in terms of tangential direction to the collision plane, ET. So how do we do this? As I said before, to find VA naught N is very easy. To find velocity of A before the collision and its component, which is normal to the collision plane, we take the velocity of A prior collision and we dot product with the unit vector, which is normal to the collision plane. In this case, VA naught is equals to V naught direction 0 dot product with EN is equals to direction 135 degrees. So we can say that this is equals to V naught cos 135 degrees, right? Which is equals to cos 135 is negative 0.707. Sorry, it's equals to 0.7071. Yeah, so we can just put this as negative 0.7071 V naught. And we also need to find out VA naught T, right? So how do you find this? As I said before, the component of the velocity before collision, that is parallel to the collision plane, is equals to the velocity prior to collision dot product with the unit vector, which is parallel to the collision plane. This one you get V naught 0 degrees dot product with tangential, right? ET is actually 45 degrees as established here. So dot product 45. So what we are doing here essentially is just that we are trying to find out what is how do we resolve the velocity component before collision into the EN and ET direction. What we are doing is just purely trying to find how to resolve the velocity prior to condition in the EN and ET direction. Why do we want to resolve the EN and ET direction? Why do we do that? For the previous question, we do the same thing too. Why do we do that? We do that because we know that to use the equation for coefficient restitution, we need to know the information in the EN and ET direction. Simple as that. So in this case, cos 45 is equals to 1 over sec 2. 1 over sec 2 is just equals to 0.7071. Same thing. So yeah, cos is what's it called? Parallel. So in this case, let me see, does it make sense? Yes, it makes sense here. Okay. So this is 0.7071 V naught. So in this case, from these two things, we can rewrite velocity of A naught before collision is equals to negative 0.7071 En plus 0.7071 Et. Alright? So I did not put in the angles here so that you can better understand what's going on in this situation here. Now how about VA1? So how about VB? Let's do VB naught first. Now, please note VB naught is 0 before collision, so it's good for us, so we can just say that it's 0. So it means that in this case we can say that VB naught N is 0. We can say that VB naught T is also 0 because the total velocity is 0 no matter what component in any direction is also 0. So we can just put this. This is a very big convenience for us. Okay, so we have already solved the before collision situation. Now, what about the after collision situation? The after collision situation, same thing as usual. We must say that VA1 is equals to VA1N En plus VA1T Et. So just go through the motion and copy down the copy down the numbers and the symbols. Yeah. So in other words, we are trying to just lay a foundation work to claim that the final velocity of A and B respectively will be resolved in the En and Et direction. That's why we just write this thing down. The main reason to write this thing down is to understand that we need to resolve the final velocity in the En and Et direction. But however, we still cannot solve this yet. Okay. Also, by the way, a bit of mistake here. This has the unknown Vn inside. Right, there's this unknown Vn inside. Right, this is very crucial. Now, after you solve these two parts, so let's take a look at how many unknowns we have now. V0 is not considered an unknown because we actually want to represent everything in terms of V0. So, in this case, our unknowns. Let's take a look at how many unknowns do we have. Unknowns. We have VA1N as an unknown. We have VA1T as an unknown. We have VB1N as unknown. We have VB1T as another unknown. Oh my god, there are so many unknowns here. So it means what? It means that we need to have some other equation. We have to have some other equation to actually solve all these unknowns that's available here. So how do we solve this equation here? Now, interesting enough, we can actually apply conservation of momentum and the coefficient of restriction equation. So first of all, let's apply the first equation here, the equation of apply the equation for the coefficient of restitution. So the equation for this coefficient of restitution, how do you apply it? So first of all, using the formula, we know velocity of A1 normal to the collision minus velocity of B1 normal to the collision is equal to negative E velocity of A0 normal to the collision minus velocity of B0 normal to the collision. Now, what is VA1 naught? VA1 naught, something we know, right? VA1 naught is just VA1 normal is something we don't. This is something we don't know. VA1 normal is something we don't know. VB1 normal is something we don't know either. Negative E is 0.8. Now VA not normal. VA not normal is something we have here. It's just negative 0.7071 V naught. So this is just negative 707. Negative 0.7071 VA naught. And this is actually essentially 0. This is minus 0. So this is not V naught, sorry. This is just V naught. The term that we want to represent everything in terms of this. Okay? So in this case, we have the first part. We successfully say that V, so we can simplify this by multiplying the 0.8 inside. So after you multiply the 0.8 inside, so 0.71 times 0.8 negative, so it's just 0.5656 0.5657. So 1.7 V naught. Here we go. Now, this is the first equation we have. The first equation we have that we solve using coefficient of restitution. Now, can we have another equation? Of course, we can have conservation of linear momentum. Now, when we want to use equation for conservation of linear momentum, we need to see where do we draw the boundary. Let me repeat, we need to see where do we draw the boundary. So where can we draw this boundary? Now, apparently, let's take a look at this question here, this part here. We can draw the boundary about A, right? We can also draw a boundary about B. We can also draw a boundary about A and B. So let's draw a boundary about A first. If you draw the boundary about A, we can see that the external force is always normal to the collision plane. During collision, the external force is, the collision force is really large, so that is the only force we consider during calculation. Now, you can see that when A actually collides with B, the external force experienced by A is only perpendicular to the collision plane. In other words, the external force experienced by A is only in the EN direction. If the external force is only in the EN direction, it means that if the external force is only in the EN direction, it means that momentum is conserved in the ET direction. If the momentum is conserved in the ET direction, it means that velocity of A in the ET direction before collision is equals to the velocity of A in the ET direction after collision. Okay, I know it's a bit fuzzy here, but let me repeat. So, when A collides with B, if we were to look at A as only a system, in other words, we actually try to draw a boundary, system boundary across A. If you draw a system boundary across A, the forces acting on A is only along the EN direction, right? The force acting on A is along the EN direction, because the collision force is the only force that we're concerned about. However, there are no forces acting along the ET direction. There are no external forces acting along ET direction as far as particle A is concerned. If this is what particle A is concerned about, this means that we don't have to actually take into account the forces acted by particle B on particle A. So if that is the only external force acting in the EN direction, this means that momentum along the ET direction must be conserved, and we can say with confidence that VA naught tangential prior to collision is equals to velocity of A after collision, which is tangential to the collision plane. Okay, so this thing is derived from the momentum conservation equation. If you don't know what I'm trying to say, please take a look at the previous question. I do the derivation. So from this part, from the conservation of linear momentum, we can say that velocity of A before collision, which is actually tangential to the collision plane, is equals to velocity of A after collision, which is tangential to the collision plane. So in this case, we can say, since VA naught T is equals to what? Is equals to 0.0701 V naught. So we can just put this one as 0.7071. 0.7071 V naught. That's the equation. So same thing goes here. Since we can draw our system boundary across particle A, we can draw a system boundary across particle A. It means that we can also create another conservation of linear momentum by drawing a system boundary across particle B. So in this case, just write this off. So we try to draw a system boundary across particle B. So let's say we try to draw a system boundary across particle B. If we were to draw a system boundary across particle B, the only force that's acting on particle B, on the system boundary particle B, is actually a force, which is a collision force, and this collision force is also along the direction which is normal to the collision plane, right? This collision force is along a direction which is same direction as the normal to the collision plane. In other words, this external force experienced by particle B is only along the EN direction, and there are no external force experienced by B along the ET direction. So we can also say that the momentum of particle B is conserved along the ET direction. If the momentum of particle B is conserved along the ET direction, it means that MB VB naught T is equals to MB VB1T, right? B naught and B1 denotes the velocity before collision and velocity after collision, which is tangential to the collision plane. So since we know that this one can cancel off. It means that we can find that VB naught T is equals to VB1 T. Right? Very interesting. So let me just bring this downstairs because it's better to write down there. So in this case, we can say that VB naught T is equals to VB1 T, which actually is equals to 0. So this was formed by treating A as a system. This equation was formed by treating B as a system. Okay, so now we have 3 more equations, right? So let's see what are the things that we have now here. So we have this in an equation, but think about it. We have 4 unknowns, right? We have 4 unknowns here. If we have 4 unknowns here, we only have 1 equation, 2 equation, and 3 equation, right? We still cannot really solve all these things. So in other words, we need 1 more equation. Now the third equation can form by actually drawing a system boundary across the whole what is it called, particle. So we draw a system boundary across particle A and B. If you draw a system boundary across particle A and B, the collision force, which is so important, has now become an internal force. When the collision force becomes an internal force, it means that the momentum must be conserved. Let me repeat. Now we draw a system boundary across A and B itself. So the collision force now becomes an internal force. When the collision force becomes an internal force, it means that we conclusively prove that the momentum of this system must be conserved because there are no longer any external force acting on it. When there are no longer any external force, we can say with utmost confidence that mass, let me just repeat. We can say that mass of A times velocity of A plus mass of B times velocity of B before collision is equals to mass of A times velocity of A1 after collision plus mass of B times velocity of B1 after collision. Okay, so this equation can be obtained by treating A and B as a system. Do you see the beauty of this method of solving now? So the coefficient of restitution actually gives information about the collision, but the conservation of linear momentum when applied at different methods can give us 3 equations as a whole, because first of all, we can draw different boundaries, and by treating different things in the system, momentum is conserved at different ways, and we draw the whole thing as a system, the momentum is conserved for all the system here, right? So let's try to solve it in this model. So we know that A and B are both identical balls, so we know that MA equals to MB, so we can just actually rub off MA and MB. Just cancel this thing off because MA and MB are the same velocity. So if we have already established this, let's try to do the equation. First of all, let's ignore this term first. Let's just ignore this equation and let's just see what are the things that we have. We can conclusively say that we have, let me see. Okay. So what we have now here, we have VA naught, we have VB naught. We don't have all of VA1, we don't have all of VB1. So let's put all the equations inside here. So VA naught is equals to what? Is equals to this term, right? So this term is equals to VA naught. I'm going to lazy to copy it, so let's copy everything down here. Copy and paste it down here. So this is actually our what's it called? VA naught plus or VB naught, which is equals to 0, and is equals to, now what is your V1? VA1 is this whole thing here. Okay. However, our VA1 is we have some progress on our VA1, right? So our VA1N is something that we haven't checked out yet. VA1N, just retain it. Our VA1T is equal to 0.7071 V naught. So this is equal to 0.7071. Let's call it V naught E T. Look at that. Now, how about Yeah. Okay. Yeah. That's what I got for VA1. Right. How about VB1? VB1, do we know anything about VB1? First of all, we do not know anything about VB1N. Yeah. But we know something about VB1T, right? VB1T is precisely this one. This is VB1T, which is 0. So we know this is only VB1N is like this. Now, we take a look at this equation, and we can actually equate the normal term, right? If we equate the normal term together, we can see, if we equate the normal term together, means that we ignore the, what is it called, ET term. We only equate the EN terms. If we equate the EN terms, what we get is that negative 0.7071 V naught is equals to VA1N plus VB1N. So, do you know how I get this equation? This equation was obtained by equating the EN terms. Means we only take out EN term. We compare this EN term and this EN term. Because obviously, the EN term here is formed by the combination of these two EN terms. The ET term here is formed by the combination of these two ET terms, which actually is equal, so we can cancel each other. But they are equal, cancel each other. So this thing will resolve into this equation. And voila, we got a new equation. So from this equation, we can do a simultaneous equation with this coefficient of restitution here, right? Let's bring down this equation from. So now we have this equation, equation 1, and this equation is equation 2. So from equation from 1 and 2, we see, let's just copy everything down. And you can see both these things. Right? You can see both these things. So for equation, actually this is not needed. We can just simplify this one. Cancel this out. Cancel this out. And we can shift this to here. Alright. Now, we actually have both these equations. And by combining both these equations, we can get our answer. And there you have it. That's basically what we have done all together. We have managed to solve this equation. Now, I know it's complicated, but let me just allow me to re-explain what we are trying to do here. Now, first of all, I lay out my equation first. You see, the flow of this whole question is actually very smooth. First of all, we know it's a collision question. We know it's a collision question. We try to find out the initial velocity before collision and the final velocity after collision. And we resolve the initial velocity in the EN and ET direction. We resolve the final velocity in the EN and ET direction. We lay out all the things that we have. For the initial velocity, we try to resolve it in the EN and ET direction. We get these two terms, and then we found these 4 set of equations. Now from this 4 set of equations, we know that we have 4 unknowns. If we have 4 unknowns, apparently we need 4 equations. So the first equation was formed by the coefficient of restitution. There's always one equation that's given out by the coefficient of restitution. So that is available in here. Now the other equation, most probably, was given out by the conservation of linear momentum. Now, how do we come out 3 equations from just the conservation of linear momentum? That is simple. First of all, we just draw a boundary at A. Treating A as a system, we get 1 equation. We treat B as a system, means that drawing a boundary across B as a system, we get another equation. Now, if we draw a boundary across A and B, treating A and B as a system, we get another equation. Now, I have to stress that I cannot stress this enough. The reason why, when we draw a boundary across A and B, we can have a conservation of linear momentum is because if we draw a boundary across A and B, there are no external force acting on A and B. Because in this case, the only important force is the collision force, and the collision force in this matter is an internal force. We do not consider internal force during conservation of linear momentum. So in that case, we only consider external force, and if we only consider external force, momentum definitely is conserved. So in that case, we actually have the third equation. Now, from the third equation, we can actually expand by subbing in all the things that we know about VA0, VB0, VA1 and VB1, and we get this equation here. From this equation, we realize that we can cancel these 2 terms, which is same the left and right side, and we have another new equation in terms of VA1N and VB1M. Now, this is our 4th equation. So we got 1 equation, 2 equation, 3 equation, 4th equation, and this 4th equation is formed by putting in the information on these 2 equations. So mathematically speaking, We just need two equations now. So the two equations we use is this equation, which is a result of the what is it called, conservation of momentum across treating A and B as a system. And the other equation is the one that we haven't used, is the equation of coefficient of restitution. From these two equations, do simultaneous equation, you will get this answer. So at the end of the day, what have we learned? For collision question, find the coefficient of restitution equation, find the conservation of momentum by drawing different boundaries, and eventually do simultaneous equation across all these things, and you will get the final answer. Right? So after that, let's go on to tutorial 10, question 4. Okay, so now we are on to tutorial 10, question 4. Now for tutorial 10, question 4, there's a few things that we have to, take note. For tutorial 10, question 4, right? Now we're talking about constrained collision. For constrained collision, we are trying to say that in this case, for constrained collision, the motion of one of the bodies or particles which is undergoing collision is forced to move in a certain direction after collision. Let me repeat. A constrained collision means that the particle or the body is forced to move in a certain direction after collision. So if a particle is forced to move in a certain direction after collision, it means that there must be a reasonable force, a reasonably large force, which is comparable to the collision force. When you have such force which is comparable to the collision force, it means that when we apply the conservation of momentum equation, we have to be very, very careful on the forces that's available, because these forces cannot now not be neglected. Okay, usually we say that during collision, all the other forces are neglected, but in this case, because we have another force which constrains the motion of the particle, of the motion of the body, those forces could not be neglected anymore. When those forces could not be neglected, they must be taken into account when we apply the laws for conservation of linear momentum. Right? Now, here is it. Let's take a look. A sphere of A have mass of 2 kg released from rest. It strike the surface with a mass of this wedge with a mass of 6 kg and velocity of 3 meters per second. The wedge, which is supported by rollers and may move freely in the horizontal direction, in other words, is constrained to move in the horizontal direction, is initially at rest. Note that theta is equal to 30 degrees, and the coefficient of restitution is 0.8. Determine the velocities of the sphere and the wedge immediately after the impact. What is the velocity of the sphere and the wedge immediately after the impact? So how do we solve this question here? So, wait a minute. Let's take a look at something. Okay. Now, so to solve this equation, the one thing we need to know is that first of all, it's also a collision question. When it's a collision question, as a rule, we always want to first of all find the EN and ET direction. After we find the EN and ET direction, we will try to resolve the initial velocity and the final velocity in the EN and ET direction. So in this case, I will denote this direction. I don't want red. So what I want is actually black. I denote this as my ET direction, and I denote this direction in my EN direction. So apparently, ET is actually equals to negative 30 degrees, right? And EN apparently is equals to 60 degrees. That's the both thing that we have. Very interesting stuff we have. ET is negative 30, EN is 60 degrees. Now, here's the most important part. Here comes the most important part. Now, how do we actually solve this equation? First of all, to solve this equation as a full, we need to find velocity of A, right? Before collision. Velocity of A before collision. Now, what is the velocity of A before collision? So in this case, they gave us it's actually equal to 3 meters per second, and it's pointing downwards, negative 90 degrees. This is a given. But however, we always want to represent this thing in terms of the normal direction. And we always want to represent this thing in the tangential direction. Okay, that is always our rule. We always want to represent velocity in the EN and ET direction. Okay, now how do we find it? So let me just revise it one last time. the velocity of A, the component of the velocity of A before collision in the direction which is normal to the plane of collision is equals to the velocity of A before collision dot product with EM. And in this case, I can confidently say this is 3 negative 90 dot product with direction of 60 degrees, which is equals to 3 cos 150 degrees. And this can be denoted as cos 150 is equal to sec 3 over 2 actually. So actually I can just put it as 3 times square root 3 divided by 2. Okay, and it's a negative because it's more than 90 degrees and less than 90 degrees. So let's check. Yes. And my VA naught T on the other hand can be found by dot producting my VA naught with a tangential direction which is parallel to the collision plane. In this case, my VA naught is actually equals to 3 direction negative 90 degrees dot product with ET. Now what is ET? ET is definitely equals to 60 degrees. 60 degrees. So if ET is 60 degrees, ET is negative 30. So, oh yeah, my bad. This shouldn't be outside. It's a very big mistake here. It should be inside. It's negative 30 degrees, not negative direction 30. Okay, that's totally my part. Okay, so now let's put it here like that. And from there, we can immediately say that it's equal to 3 cos negative 60 degrees, which is actually just 1.5. Okay. Now, so we have solved for VA naught T, and we have actually solved for VA naught M. So in other words, let's just make everything nice. We know that velocity of A naught is equals to negative 3 direction sec 3 divided by 2 direction EN plus 1.5 ET. This is literally what we have right now. So since we have this information, we can proceed to find VB naught. As a rule, always try to find the final initial velocity first. Always try to find that. So VB naught is apparently 0 because it actually it's at rest. It's initially at rest. It's given in the question. So in this case, we can also say my VB naught T is 0, and my VB naught M is 0 because when the final velocity is 0, everything is 0. Now, that's before collision. How about after collision? After collision, nobody knows what's going on. However, we know the velocity of B of A1, because okay, after collision, the ball can actually go in any direction. It can actually go in any direction it is. So for VA1, we never know what is the constraint. Let me repeat again. For VA1, we never know the constraint. So for VA1, we can say D is just equals to VA1 and EN, like what we have done before, and it's equals to VA1 T ET, like what we have done before. Just write it down here, just to indicate that we will resolve the velocity of A after collision in the EN ET direction. Now how about VB1? Now this is a very interesting thing to note. For VB1, right, we cannot put this easily, because we know that for VB1, it will definitely go in what? VB1 will definitely be in the horizontal direction. And we can assume a direction, just assume that VB1 will go in, let's say in this case, when it hits down here, apparently B will go behind, right? So we can just assume that VB1 will be in the direction of 180 degrees. However, we also still want to represent it in this form. We also want to represent it in this form. VB1M EN plus VB1T ET. So in this case, we have to utilize what we learned before. So in other words, we can always say the VB1M is equals to velocity of B1 dot product with EN. Same understanding. The velocity of B after collision in the direction of normal to the plane of collision is equals to the velocity of B1, the B after collision, dot product with direction EN. And from there, we can get something quite interesting. Direction EN is actually equals to, let me see, 60 degrees. We have denoted as 60 degrees. And this thing means that it's VB1 cos 120. Cos 120 is just negative VB1 over 2. Right? Because it's more than what is it called, 90 but less than 180. Now, how about VB1t? VB1t is something interesting. Now, VB1t is the same thing. It's equals to velocity of B1 dot product of ET, a direct unit vector in the direction which is parallel to the plane of collision. In this case, we can just put out the math. 180 degrees dot product with negative 30, if I'm not mistaken, which is actually equals to VB1 cosine 210, which in this case, cosine 210 is equal to negative 3 over 2. So we got what is it called, negative VB1 square 3 over 2. Let me see if this makes sense. Well, it makes sense. So in this case, when you start it back inside here, you can say that with great confidence that VB1 is equals to negative VB1 over 2 EM plus negative VB1 sub 3 over 2. ET. And it can also be expressed in terms of VB1 direction 180. We need both these expressions eventually. So let's see what are the equations we have. So till now, let's look at the what equation we have. Let's make everything y is equal nice and y is equal orderly. We have equation for VA0, right? We have equation for VA0. Let's just place it down here. We have equation for VA1, which is we have equation for VA1. We have equation for VP0, which is 0. But this is actually one of the simplest equation. And we have equation for VP1. So let's see what are the unknowns that we have. So from here, let's take a look at what the unknowns that we have. The unknowns that we have is actually, we have VA1N as unknown, one unknown. We have VA1T as unknown, two unknowns. And we actually have VB1 as an unknown. Oh, interesting stuff. We only have 3 unknowns. Take a look at that. We only have 3 unknowns. Why do we have 3 unknowns but initially we have 4 unknowns? In most cases, the previous question, we have 3 or 4 unknowns. Why in this case we have only 3 unknowns? We have only 3 unknowns because this is a constraint equation. We know the direction of velocity of VB1 after the collision. If we know that particular quantity or property, we can actually represent the velocity in terms of En and Et of VB1 in terms of VB1's magnitude. That's what we're doing here. That's why we only have 3 unknowns here. So since we only have 3 unknowns, we need to have 3 equations. The first equation that I always want to apply definitely is the equation of coefficient of restitution. So let's apply the coefficient of restitution. So the coefficient of restitution equation. Now how do we apply this equation here? Now to apply this equation here, first thing first, just recite the formula, which is just equals to VA1N minus VB1N is equals to negative E VA0N minus VB0N. Simple. So we just plug in whatever we have. What is VA1N? VA1N apparently is something we don't know. VB1N is something that do we know what is VB1N? No, actually we do know what is VB1N, right? VB1N is equals to negative VB1 over 2. So it's just equals to negative VB1 over 2. Negative E is 0.8, put it in. VAON is equals to negative 3 times 3 over 2. Something just calculated before, if not just rewind the video and see when do we do it. Now VB0N is something that we do not know, that we know is 0, sorry. So it's minus 0. So to put everything together, tap everything together on, and eventually you have VA1N times 2. Let me see how to solve this equation. Plus VB1 is equals to the minus cancel off, the times 2 cancel the 2 inside here, and 2.4 square root 3. Yeah, that's what we have here. So this is the first equation we have. 2.4 times square root 3. Mathematical notation wise, not that great, but never mind. So 2.4 times square root 3. Okay? So this is the equation that we have obtained by using coefficient substitution. But it's not enough, so definitely we need to use conservation of linear momentum, right? Because this equation alone is not enough. So first of all, conservation of linear momentum. How do we do this? Now, as far as conservation of linear momentum is concerned, we have to draw boundaries. So definitely in this case, since as I see for A itself, when A reaches here, when A actually, so let's see, when A actually reaches here, you can see, so when A actually reaches here, what happens is that there's actually only one force acting on A, right? Which is the collision force. The collision force. FC, the collision force. And this collision force acts along EM. It acts along the direction of EM. So, if today I were to draw a system boundary across particle A, the external force experienced by this system is only the collision force. The gravitational force we can ignore because the gravitational force is small, is petite in comparison with the external force, which is by the collision. In this case, this external collision force only acts along the EM direction, which is the direction perpendicular to the plane of collision. So in other words, there are no other forces along this ET direction. There are no external force along the ET direction. So momentum is conserved along the ET direction as far as the boundary on the A is concerned. And repeat, the momentum along the ET direction is conserved if we were to draw the system boundary across particle A only. So we can say that mass of particle. So we can say with utmost confidence, we can say that the mass of particle A before collision times the velocity of particle A before collision in the direction which is parallel to the plane of collision is equals to the mass of particle A times the velocity of particle A. Let's make it better. So because of conservation of momentum along this ET direction, you can say the mass of particle A times the velocity of particle A before collision, which has a velocity in the direction tangential to the ET direction, is equals to the mass of particle A times the velocity of particle A after the collision, which has a component tangential to the ET direction. So we can cancel this one, and we have formed one equation, right? Remember, the momentum is only conserved along the ET direction. It's not conserved along the EM direction, because along the EM direction there is an external force Fc. So in this case, we can just shift this equation into here. So COM, the first thing, you know that the velocity of A before collision tangential to the along the direction of collision is equals to the velocity of A after collision tangential to the along the direction of what is it called, plane of collision. So this is done if we take A as a system. Now, the second equation can be obtained if we take the whole thing as a system. In other words, the second equation, the second COM, the second conservation of linear momentum equation can be obtained if we take both. If we take both, you see, A and B as a system. We take everything as a system. If we take everything as a system, the collision force becomes an internal force, right? The collision force becomes an internal force. However, that is something that's extremely interesting to happen here. Although the collision is the what is it called become internal force, we don't have to take into account the collision force. There is also another force which is significant during the point of collision and cannot be neglected. That force is the force that constrains B to move in the horizontal direction, and that particular force is actually this normal force, the normal force that acts upwards. This normal force that is contributed by the table onto this wedge here that acts upwards is actually the force which constrains wedge B to move along the horizontal direction. Please take this very seriously and very carefully. First of all, what I've done is that I draw my system boundary across both A and B. I draw my system boundary across both A and B. And now my collision force has become an internal force. When my collision force becomes an internal force, it means that I don't have to take into account the collision force when I'm looking at the conservation of linear momentum, because the collision force is not an internal force. All I have to see is that is there any other significant external force? Now, of course, there's also the weight, the gravitational pull, but the gravitational pull is small in comparison with the collision force, so we can ignore it. However, there is still another force which is also significant and could not be ignored, and this force is known as the normal force exerted by the table or the wedge B. Now you might ask this question, why is the force Fm significant and could not be ignored? Because this force is exactly the force that constrains B to move in the horizontal direction. Without the force during the collision, B would have moved into the table. The reason why B could not move into the table is because we have this normal force. We actually force this this wedge here to move horizontally. So as I say, this is a constraining collision. For a constrained collision, forces which are directly involved in effecting or realizing the constrained motion, which in this case is this Fm here, cannot be ignored during collision. So in other words, the momentum of A and B, if I draw the system boundary, if my system boundary encapsulates both A and B, the vertical momentum is actually not conserved. Let me repeat. If I draw my system boundary across A and B, my vertical momentum is not conserved. However, my horizontal momentum is conserved, because horizontally there is no external force, but vertically there is external force. What external force is that? My Fn, my normal force, contributed by the table onto the wedge. So in this case, only my horizontal momentum is conserved. So in other words, I can say, if I were to draw my momentum curve, my system boundary across A and B, mass of A times the velocity of A before collision, however, in the horizontal direction, plus mass of B times the velocity B before collision in the horizontal direction is equals to the mass of A times the velocity of A after collision in the horizontal direction plus mass of B times the velocity of B after collision in the horizontal direction. So how do we take a look at this? So now there's something very important I want you to take note, and please take note of this very, very carefully. When we talk about horizontal direction, let's try to simplify this equation first. How do we simplify this equation? So first of all, initially the A is going downwards, right? So there's no horizontal velocity, so this is definitely 0. So apparently this is 0. Now initially it's static, so this is also 0. So it means that we need to find MAVA1H. So now, what is MAVA1H? So first of all, what is VA1H? VA1H is actually the horizontal component. Let me repeat. VA1H is the horizontal component of velocity A1. What is the horizontal component of velocity A1? Is actually equals to velocity of A1 dot product with 0 degrees. Right? What is velocity of A1 dot product with 0 degrees? Take a look at this. Velocity of A1 dot product with 0 degrees, if we for the formulas, we can find that it's actually equals to VA1 N En plus VA1T ET dot product with 0 degrees. Now, it is a painful journey, but actually it just dot product with 0 degrees, so it's very simple actually. So just get generally speaking VA1M cos En is equals to what is it called, 60 degrees, so just cos 60 plus VA1T cos negative 30. So if we do this formula, you'll find just VA1M divided by 2 plus square root 3 over 2 times VA1T. Yes. That's all you have. Simple as that. Okay. Now, this is what, so the VA1H means the horizontal velocity of A after collision. So how do you find the horizontal velocity? Just resolve it to the horizontal direction, which is dot product with 0 degrees, or just cos everything. Same thing here. What is VB1H? VB1H is the velocity of B after collision in the horizontal direction, which is also equals to VB1 dot product with 0 degrees. Now please do not take this VB1H as equals to VB1 directly. VB1 directly, however, is not the same. How do I know? Let's just prove it. VB1 dot product with 0 degrees equals to VB1 direction 180 degrees dot product with 0 degrees, which is equals to VB1 cos 180, which is equals to negative VB1. From these two equations here, we sub inside here, we got the final equation 0. So from this equation, we sub inside here. From this equation, we sub inside here. Eventually, we have the equation 0 is equals to MA VA1N over 2 plus sub 3 over 2 VA1T minus MB VB1. Okay, so let's take a look at how many equations do we have. So we have the first equation. This is our first equation. It's our first equation. This is the equation that is obtained from the coefficient of substitution. First equation, just and our second equation, which is this one. When we take A as the system, this is our second equation. And this is our third equation. This equation is what equation that happens when we take A and B as the system. When we take A and B as system, this is what we have. So just copy everything here. This is actually our third equation. So this is our third equation. So let's see how many unknowns do we have. Now MA and MB is given in the question, definitely. If you don't have that, you cannot solve it, right? So look at that. How many unknowns do we have? We have VA1 TN as one unknown. We have VA1 sorry, let me apologize for VA1M as unknown. We have VA1T as unknown. Now VA not T, this is actually a known number. VA not T is actually here. VA not T is actually this thing is 1.5. I think I should have put that first so that we can reduce any confusion. So this is actually just 1.5. Okay, VA not T is something that we know. It's just 1.5. You can get it from here. Sorry for the confusion. So we have VA1N is unknown. We have VA1T as unknown, and we have VB1 is unknown. So we got 3 unknown and we got 3 scalar equations. So since we got 3 unknown and 3 scalar equation, apparently we can solve this equation with ease. Okay, so now we're going to take a look at the next question. So for this question, just want to emphasize what are the things that we are doing about. So first of all, we saw this question, we know it's a constraint equation. We know it's a constraint equation. First thing we do, is a collision equation, resolve the initial velocity before collision and final velocity of the collision into the en and et direction. But since it's a constraint equation, it is constraint equation for a reason. We always want to make sure that after the collision, we can know the direction of VB1. And hence we have all these things here. Just rewatch the video if you don't understand what I'm trying to say. After that, we will have all these equations that's there for us. Then we try to set up our equation to solve this problem, which involves the equation for coefficient of substitution. Always give us one equation. The equation for conservation of linear momentum, in this case, gave us 2 equations. The first equation was obtained by taking A as a system, and we get VA naught T is equal to VA1T, which is equal to 1.5. And the second equation was formed by taking both A and B as an equation. When we take both A and B as the system, we need to understand that the vertical momentum is not conserved, but the horizontal momentum is conserved. When the horizontal momentum is conserved, we can say with confidence that we can equate the horizontal momentum together. And we have to know the VA1H and VB1H, which is the horizontal velocity of A after collision and horizontal velocity of B after collision respectively, which can be found by dot producting the velocity of A after collision with 0 degrees and the velocity of B after collision with 0 degrees. Represent everything in terms of VB1 and VA1T and VA1N. Lay out the equation, lay out the true equation, do simultaneous equation, get the answer. Okay, please take some time to do this question and to understand what's going on, because it can be quite tedious for this equation. Okay, so we'll go to the next equation. For the next equation, I will just I will just briefly explain it, and after that we will continue. Okay, so now apparently we're going to continue tutorial 10, question 6. So this question itself, I'm not going to do a lot of explanation, just going to briefly glance through it. I'm just going to glance through it so that you guys know what's going on. So in this case, a 1.5 kg sphere moved to the left with a velocity of 1.5 meter per second. I don't know, I think it should be 1.5. And when it strikes the inclined surface at the 4 kg block, which is a rest, the block is supported by rollers and is attached to a spring of constant K equals to 5 kN per meter. So, knowing that the coefficient of substitution is 0.75, I'm getting friction, determining the maximum deflection. So, I'm not going to solve the maximum deflection part. Apparently, if you can find the velocity of the block after collision, you can use the energy method to find the maximum deflection of the spring. So, my main purpose here was to guide you to find what is the velocity of the block after collision. Now, to find the velocity of block after collision, it's a collision question. So, apparently, just give it some notation. We say that this particle is A, the block is B, and of course, when doing a collision question, we always want to first define our EN and T direction. So this is my EN direction, this is my ET direction, just because I like to set it that way. So if this is my ET direction, if the gravity is 30 degrees, if this is 30 degrees, it means that through some understanding, I can know that. I'll just make it clearer for you to see. This is my EN direction, this is ET direction. So for EN direction, this is 30 degrees, and this is 30 degrees. We know that this is 90 degrees, so this is also 60 degrees, right? If this is 60 degrees and this is 90 degrees apart, this must be 30 degrees. So we know that our EN is equals to 30 degrees, and our ET, which is always 90 degrees apart from EN, is equals to 120 degrees. Okay, and you can just generally speaking just find the answer you have for that miraculously. Okay, now this is just geometrical analysis. You can just find E and ET easily. So definitely the first step you should do is, first of all, find velocity of A in terms of is equals to 1.5 meter per second, and direction to the left, so we just have 80 degrees. And you can definitely find VA, let's see, you can find velocity of A, 0, before collision, in EN direction, plus VA naught in the T direction. How to find it? I'm gonna leave it to you. ECT. Okay. Now, then of course, since the block is initially at rest, okay, notice 0, and we also know that VA naught VB naught n is 0, and we know that VB naught t is also 0 because initially it's 0. So when 0, nothing is something that we are concerned about. So after collision, please take note, after collision, A can move in any direction. So VA1 is always denoted in VA1n plus VA1t. And there is no exact direction of where you should move. Okay. However, for VB1, it's a constrained motion. If it's a constrained motion, it is very apparent that if it's a constrained motion, it means that the velocity of VB1 will definitely go horizontally. So in this case, going to the left. So we can say that it's 180 degrees. So in this case, it means that we can find VB1n En plus VB1t et, right? And this En, VB1n and VB1t can be represented in terms of VB1. And we repeat, the VB1n, the VB1n, and the VB1t, the VB1n and the VB1t can be represented in terms of VB1. Okay, and that's something that you have to do. After you establish all the equations here, eventually you need to have those you should end up with, if not mistaken, 3 unknowns. For the 3 unknowns, you need 3 equations to solve. The first equation to solve is the coefficient of restitution. Coefficient of restitution equation. That one you can solve it easily. The second equation should be from a conservation of linear momentum of A as a system. And the third one will be conservation of linear momentum of A and B as a system. In other words, we draw the boundary curves across A and B. Now, some of you might ask, why can't I just draw a boundary curve across B? Well, the answer is because if you draw a boundary curve about B, look at that. There are 2 forces which are prominent. The first force is this normal force, and the second force is this collision force. It means that the important forces, the prominent forces acting on B during collision it occupies or has a component in all directions. Because the collision force is in this direction, normal force is in this direction. So horizontally or vertically, no momentum is conserved. So we cannot just take a system boundary across B. We have to take a system boundary across A and B because we want to ignore these collision forces and only take into account the vertical forces caused by B. Right? If you take into account the vertical forces caused by B only, it means that only these vertical forces here is the external force, and if this vertical force is the only external force, it means that horizontally momentum is conserved. So we have that in mind. So it means that in this case, one of our equations is formed by taking A and B as a system. One of the equations is taking A as a system. The other equation is taking the coefficient of restitution. From the C equation, you can solve the 3 unknowns. You can find the final velocity of B after collision, and eventually, through conservation of energy, you can find the deflectionless spring. So that's how you should solve this question. It's very similar to question number 5. Okay, is it question number 5? That is similar to question number 4. So it's very similar to question number 4. Okay, so that's all of it. So thank you very much. Today's lesson we will end it here. Okay, now thank you very much.